Hello, Chem 115 students. It's time for a quick mini lecture on integrity to help cover some topics that we won't have time to do in class. Many of you have discovered this on homework by now, but there are some questions about hydrates. Hydrates are substances that have water molecules directly in their crystals, and they're described in their formulas telling you how many water molecules are in the crystals. Some of these compounds are this nature because the compounds themselves are what we call hygroscopic. They attract water from the air. The little packets of silica gel that you often find packaged with leather goods or sometimes electronic equipment is exactly that kind of thing where it absorbs water from the air, but hydrates are a little more specific in that. So we need to look at a couple examples. One example of a hydrate is gypsum. Anybody who's ever done sheetrock, you know what gypsum is. And it's calcium sulfate with two water molecules co-crystallized in the solid. It's called the dihydrate of calcium sulfate. And if you pose the question what the mass is that is required to get 1 mole of calcium sulfate, you have to realize how to approach the problem. The thing you have to begin with is determining the molecular weight or molar mass of the calcium sulfate. And to do that, you use your friend the periodic table and start adding things up. But then you have to add as well the molar mass of 2 moles of water, or to add in the 2 moles of water. So let's do the mass. So find your friend the periodic table, the molar mass of calcium. I'm going to do this in round numbers because I'm limited to writing with my mouse for this particular recording. 40 for calcium. Sulfur is, look it up, should be 32. And 4 oxygens is going to be 4 times 16. Those of you with a calculator or a math instinct might know that 4 times 16 is 64. That would be calcium sulfate alone, but to get 1 mole of calcium sulfate from this calcium sulfate dihydrate, 2 water molecules have to be included. So you'll add in twice the mass of water. Well, if you could think about it, 2 hydrogens plus 1 oxygen should be 2 plus 16, or 18. And with the addition of a few moments with your calculator or a pencil on paper, we can determine what the molar mass is. Pause your recording with me and do the math. If we've done our addition the same way, and I'm just using whole numbers because it's close enough for this purpose, you'll determine that there's 172 grams for 1 mole of calcium sulfate dihydrate. Now, if you needed 5 moles of calcium sulfate for something, and it came in the form of this calcium sulfate dihydrate, what mass would you need? Well, again, this is a problem where you can set up your units and make sure things cancel. Begin with the number that's given, the 5 moles, and then use the molar mass. And without too much complication, you might realize that the 172 grams goes on top because that's the mass for 1 mole, which will conveniently cancel out. And then again, this is just a calculation exercise to determine the number of grams needed to get 5 moles of calcium sulfate. Pause your recording and do the calculation with me. And I hope your calculator comes out the same as mine does, the calculation. And 860 grams would be required to get 5 moles of calcium sulfate using this dihydrate. You have a problem on your homework that looks exactly like this with Glauber's salt, except that Glauber's salt is a different compound, obviously. Calcium sulfate does occur in other hydrates. The one that's used in plaster of Paris or in these things that's shown for sculptures happens to have half a water molecule per formula, per hydrate. You only ever know what number there is by looking it up. No one's asking you to memorize them. Now, things that affect solubility are somewhat related to what you've done in lab, and so hopefully this conversation is not complicated, but it may be a useful supplement to what you might read in the book. When you have a saturated solution, which is what was done in last week's experiment, there is a state of dynamic equilibrium where the solid is constantly dissolving to make solution, and part of the solute is constantly recrystallizing to make a solid. So there's a dynamic equilibrium going on when you have a saturated solution. A little bit of solute is always redissolving, a little bit of solute is reprecipitating. So we think in terms of what actual solubility means. It's how much of a substance that dissolves in a particular amount of solvent at a particular temperature. Commonly, these things will be described as how much dissolves in 100 milliliters. And so things like, here we have sodium hydrogen carbonate, namely baking soda. You can get 9 something grams per 100 milliliters at 20 degrees Celsius. It varies with the substance. Sucrose is completely different. Sucrose has got a much more complicated formula, which I won't list at the moment, but it can dissolve to the point of 204 grams per 100 milliliters. So there's varieties of levels of solubility depending on various substances, limited by the nature of the compounds. Like dissolves, like is always related there, and solubility rules. As you may recall, sodium compounds should always be relatively soluble, and sucrose is dissolved readily in water, as you might have noticed in lab last week, because its formula has many OH groups in it, and that helps those polar OH groups interact with water for hydrogen bonds. Another factor that affects, or thing that we need to consider in describing solubility, is the fact that temperature is a very significant influence. Generally speaking, most things you're going to get them to dissolve better by heating them up, is exactly what you did in lab with the potassium nitrate. Here's a graph that shows a variety of substances as they are dissolved in water at different temperatures. So in general, most of these things are going to do what? As you heat them up, the solubility, which is the left axis, is going to generally increase. So as the temperature increases, the solubility also increases. And I'm going to abbreviate this as SOL for solubility, also increases. But it's not universally conspicuously true, which is sort of surprising. If you look at these bottom two, the cerium sulfate, weird example, and sodium chloride, it's practically no change in solubility with temperature. So it depends on the substance and some other complex factors that we're not going to go into. But in a general sense, things will dissolve to a greater extent, more grams per 100 milliliter as you warm them up. Notice up at the top here is sodium acetate, the one that we used for the demonstration in lab for supersaturation. Various examples. Again, nobody's specifically memorizing these. However, there's another graph here on the next slide that reflects the solubility of gases with temperature. And again, the solubility is the vertical axis, the left side, and the temperature at the bottom. And the general pattern here for 4 different gases shown are carbon dioxide, xenon, oxygen, nitrogen. You don't have to really know anything about why, but take a note. Do the solubilities change as you heat them up? Generally, yes. Oxygen and nitrogen, very little. But the other two are more conspicuously. The heat is going to decrease the solubility of a gas, which is why if you like carbonated beverages, you keep them cold, because the CO2 is going to escape out of them much more rapidly as they warm up. So much different than solids. The CO2 will escape from a warmed beverage more rapidly. You can think about the effects of temperature in waterways or in water solubility on organisms that live in rivers and streams. As the water gets colder or warmer, surprisingly, as it gets warmer, there doesn't change the the solubility of oxygen too much. Okay, the third thing that we need to think about here is the effect of pressure on solubility, and there's a relationship here called Henry's law. This field, you don't have to worry about the name. And this is another equation that you will get on the next exam, and it explains how the concentration of a gas in a solution is related to its pressure. It's partial pressure, and this will be provided for you, so you don't have to panic about memorizing it. And it goes like this: the partial pressure being used to express the concentration of the gas in solution, the partial pressure is going to change when the temperature changes. So if the partial pressure over the solution changes when the temperature is constant, the new solubility of the gas can be calculated by this type of relationship. So the partial pressure is related to the concentration. We will think in terms of those things. So we'll describe solubility as C, or a concentration, and P for one set of conditions being related to a concentration and pressure at a second set of conditions. This is rather straightforward as long as you pay attention to which one is the first and the second, just like we had to do when we were doing gas law calculations in Chapter 8. So let's try an example. And apologies to the fact that I can only use my mouse to draw on this slide. So if you're looking at a carbonated beverage, there's carbon dioxide gas dissolved under pressure, and it's going to leave the solution when the bottle is opened and the pressure drops. That is how come you get a pop sound when you open a carbonated beverage. If the solubility of CO2 in water is, this funny units, don't get worried about it, 0.15 grams per 100 milliliters at 1 atmosphere, what's the solubility going to be in the soft drink where it's pressurized with a pressure of 4 atmospheres? Well, what are we looking for? We're looking for solubility. What are we given is question number 1. Well, here's one pressure, so there's a pressure. This would be the second one, because the first one is the one that's given in the first, well, you can label them either way, but I'm going to call that the first one. The first pressure corresponds to this first concentration, the 0.15, so let's call that C1. And so the new solubility, a solubility is a concentration here. So the solubility that we want is going to be C2. Setting up this equation based on what was shown on the previous slide, C2 is going to be equal to C1 over P1 multiplied by P2. And if you don't know how to do this algebraically, look for the equations provided on exam 4 from a previous semester, and you'll see the equations that are given. So, not thinking too hard, the first concentration here is 0.15, and it's grams per 100 milliliters. I'm just going to leave this as grams for the moment, because it's going to get clumsy to write, but I'll make sure I'll add it at the end. And no, I won't. I'll put it in just to make sure I'm complete. All right. Not fun to write this way, but we'll make it work. Pressure 2, again, setting up your equations first and then putting in the numbers is always wise. Pressure 2, 4 atmospheres. Before you go, there you go. We don't have to write the 0.0. Always put in your units to make sure you haven't overlooked anything. And divided by pressure 1, oh hooray, fast math, it's 1 atmosphere. So having done that, you can see that the atmospheres cancel. And the answer will be 4 times 0.15, which if you can pull out your calculator, you might suddenly have the same answer that I do. It's 0.6 grams per 100 milliliters. Not tricky to do. It's just one of those things that you have to be able to set them up carefully, pay attention to which ones are 1 and 2. All right, this would have been in the report for a class, but we are not doing it this time, so just ignore this thing on the top. I wanted to make a few comments about dilutions. Dilutions are really simple to do. If you remember that moles per liter is how we define molarity, and so moles times liters equals moles. This is going to be used in lab next week, by the way, as well. Something very similar. And so the moles of something you have before you dilute it is going to be the same number of moles that you have after you dilute it. It's just that you put a larger volume there. And the way these problems are used in calculations is not difficult if you think in terms of moles being equal to molarity times liter, or moles times volume. Molarity times volume, be careful, I meant to say molarity. And the moles after you've diluted are going to be molarity number 2, volume number 2. And you have to pay attention to what your units are here so nothing comes out funny. But commonly the volumes will actually end up in milliliters for both volume 1 and volume 2. And if so, you don't have to convert to liters. So this equation can be worked quite simply to find M2 or V2 if that's what you need, with a little bit of rearranging. These again will be provided for you on the next exam, so you don't have to panic about putting them on your note card or remembering them correctly. They're not hard to use if you're careful about labeling which entity is solution 1 and solution 2. So we need to be able to do those things. The rest of the things on the slide here will happen in class later. I hope these things help you as you work on your homework. Good luck with those things, and make sure you ask when you have more questions.